Hi, good morning. My name is Arthur Moore, and today I'll be covering my report on two papers focused on propositional logic. The two papers were written by Dr. Hughes himself back in 1976, and they both have the same concept. They revolve around the dyadic partial implication propositional calculus, which I'm going to abbreviate as PIPC. I'm starting with the two variable implication one because it expands on three concepts that we have already covered in class. The first one is that we can simulate post-normal forms with just three variables. However, since we're doing dyadic PIPCs, that won't work. Also, the PIPCs, they limit us to only one connective, which is the implication, the horseshoe. And like we see in class, the only way around this is we have to encode a sequence as a composition of forms to simulate a Turing machine. A few definitions before I get started. The I is the PIPC itself, is the inference system. The rules of inference are modus ponens and substitution, which are standard rules. And the lowercase p's is the set of all propositional variables. And the capital P is all the well-formed formulas that involve P1 and P2. Well-formed formulas are just finite sequence of symbols for a given alphabet. There's a decision problem associated with this. The problem is an arbitrary member of W and P derivable in I? So some work by M. Gladstone showed that P2 cannot be derived by any dyadic PIPC, which opened the room for the question. Does a dyadic PIPC whose decision problem is recursively unsolvable exist? So this paper has two main goals. The first one is to prove the existence of it, and the second one is to categorize the degree structure of the general decision problem. That was the inspiration for the paper. The original paper Dr. Hughes actually proved that before this paper, but this paper was the first time he incorporated the Turing machine encoding into it. So he uses a quad notation to simulate the Turing machine, where the Q is the current state, A is the discriminant, 0, 1, D can be right, left, 0, 1, and then S is the next state. C is just the configuration of the machine's current status. And then we have this little theorem that helps us that C2 is the derivative of C1 if there's some sequence S1 SM such that S1 equals C1 and SM equals C2. Then we can call C1 mortal. It's going to be important for reduction. We wanted to show that we can reduce the Turing machines to our problem and then show they're both non-recursive RE and that they're equivalent. If we can do that, we can show the unsolvability of the general decision problem, and we can also categorize it, which solves both our questions and goals for the problem. Here's the encoding that I mentioned. It is very similar to what we did in class. However, notice that even though we only have one connective, the implication, we're still able to uniquely identify all of our well-formed formulas. To prove that the encoding is correct, we have to reproduce all the axioms. After that, there are only two cases. The first one where C itself is the terminal configuration of M, which is just the basic syntax, the easy part. And then the second one is whenever C1 is the immediate successor of C2 in M. So that takes a little more work, a little more because you convert them from C1 and C2. However, it's still pretty straightforward. So now we're able to fully satisfy our encoding and we can go straight into the proof. The next step is to develop the proof. To prove that they're both equivalent in a sense of many one degrees. Dr. Hughes uses 5 lemmas to build the proof. The 1 through 4 just build on top of each other, and then 5 merges all the previous 4 together. However, the intent of my presentation today is to focus on the results and the relevance instead of focusing on the proof. So if you want to check the proofs out, you're more than welcome to. I've cited this paper at the end of the presentation. And the three theorems that we can derive from it is that we can reduce halt is many to one reducible to our problem, that every non-recursive is many to one degree is represented by our problem, and every non-recursive one-to-one it is not represented by our problem. The most relevant part of it is that, like we're talking about in class, finding the degree of unsettability of a decision problem is like the biggest focus of compatibility theory. So being able to prove that not only it was solvable, but also categorize it as non-recursive RE because you reduce it from halt is extremely relevant, especially because we're talking about the 70s, and that's whenever compatibility theory was at its peak. And not only that, the encoding of the Turing machine that Dr. Hughes did over the PIPC was a different approach to what people were using at the time. So it was revolutionary in matter of the PIPC field. And personally, I really like this paper because we practiced a lot of reduction for the first midterm. And when I picked this paper, I had no idea it was going to be similar. I thought it was just going to be like robust, heavy mathematical logic. And it was really cool that you can apply some concepts from class. The second paper, like I said, doesn't take a lot of the things we'll learn in class, so I just have to explain some new things. The first one is we can call D an arbitrary PIPC, W is a one variable well-formed formula, and F is a first order formula. The big sentence that drive this paper is W is the variable if and only if F is a tautology of the first order predicate calculus. Some previous work from E. Borger uh, defined that there's two classes C and D, which are prenex, which use the for all quantifiers, and they're both reduction classes. I'm gonna get to that in a second. They're both reduction classes in conjective normal form, and they have monadic and binary. Monadic means taking one argument, and binary means two arguments. Reduction classes are they're just a class R of formulas of the first order predicate, and there exists an F of a precision theta such that it maps the first order formulas F to a meter theta F of R. And then it is only satisfiable if the mapping is also satisfiable. And that was kind of derived from M.R. Crum, which talked about F1, F2, and how F2 is the only tautology if F1 is. And then here is where this is where the main part of the paper. Dr. Hughes' approach is he defined a set D that there exists instead of the for all, and after he defined D, he defined another class C of formulas that are the negation of all the formulas in D. So as you can see, uh, C uses for all instead of there exists. Also, it uses conjunction normal form instead of disjunction normal form. So disjunction normal form is basically the sum of products. So the or is between parentheses. The or is outside of parentheses, and then the and is inside. And for the conjunction normal form is the product of sums. So the or is inside, and then the and is outside. Also, the set D has a three literal conjunction, and the set C has a ternary conjunction, which is bad. But his approach is not an advance of Borger's, it's just another take to it. It is stronger in the sense that the formula C have the binary prefixes of C1 and only have one of the binary functions of C2. However, it is also a weak result, like I mentioned, because of the ternary disjunct from C1 to C2. So it is not really an improvement, it is just a different take on the problem. And once again, um, after he defined the model, he goes straight to proving it. He develops another 5 lemmas and then the 2 theorems. I'm not going to cover the lemmas, however, the 2 theorems are he defines class D as a reduction class to reducibility and class C a reduction class to satisfiability. As I mentioned, the reducibility has to do with deriving from F to the PIPCI, and satisfiability has to do with the mapping. And in order to validate these theorems, the 4 lemmas were used. I'm only going to cover one of them because it was really important. He had to derive D. The W is derivable in D if and only if D implies W star is a tautology of the first order calculus. And to prove that, you have to consider all the instances of W. So you have to consider W as an axiom, as a substitution, and as modus ponens, which took about a page and a half to prove. However, after you do that, you just have to build on top of it and incorporate PIPCs. Although this paper was not as groundbreaking as the first one, it is still a significant improvement to PIPC research. It's a different take to Borger's approach, And personally, I really like this paper because in my personal PhD, sometimes it's a give or take. Like you have to, in order to better the results somewhere, you have to sacrifice somewhere else. Just like Dr. Hughes was able to improve borders in an area while sacrificing the other part. And these are my cited. If you have any questions, I'd love to answer them.